My name is Gabriele Bunkheila. I work at MathWorks. I'm based actually in Cambridge, but I have a worldwide role for two of our products that are possibly most relevant to you guys, which are called DSP System Toolbox and Audio System Toolbox. And this talk, it was the content of this talk. I've used it many times since the beginning of last year at AES conventions and other presentations at other universities. Hopefully it's useful, and hopefully you haven't seen it yet. And it's about using MATLAB for something that is normally not seen or perceived as the main use of MATLAB, which is real-time audio prototyping. So taking your ideas and being able to build a demo with it that doesn't depend on other fancy tools, but can be contained and easily developed with MATLAB, right? What else is there to say? Well, a couple of words about me. I've been working about 10 years with MathWorks. MathWorks, obviously, you might know the makers of MATLAB. When I joined about 10 years ago, here I used to go around the UK and talk to people who wanted to apply MATLAB to solve their signal processing problems. And now I work more focusing on those two products. I'm a technical person, physicist, and then an engineer for PhD. But now I work in a weird discipline that people in academia usually don't tend to know, which is product management. What does that mean? It's a technical role to do with a strategic direction, feedback into development, talk to people who use these specific products and try to understand what they need, right? As well as working on more fun stuff, so like demos and things like that, or website content. Right, so let's get started. I've got a few slides. Most of the session will be about tutorial in MATLAB, so code. You more than welcome to interrupt me and ask questions, because otherwise you'll have forgotten by the end of the talk. The code will be gone. So just if you've got something in mind that relates to the code, raise your hands, and we can discuss about it. I plan to be talking not uninterruptedly for about an hour 15, an hour 20, something like that. Okay.
I'm going to have to go. I've got an experiment at an hour's time.
I won't get offended. Free go in and out, as you please. All right. And if you want afterwards, if you're interested in the code, I'm more than happy to share it. I don't know if we could arrange some handover afterwards, or even offline. Send me an email. That's my email. All right. So first of all, who am I speaking to? Let's see if you can recognize yourself in this kind of target for this talk. The idea is that you are supposed to be familiar with DSP, algorithms, discipline, and a bit of MATLAB. Do you feel you can recognize yourself there? Good. All right. And not only that, but that's a requirement. What about target and interest? I think the idea is if you develop algorithms for research or other purposes, and you need to prototype them in real time. So let's take a look at this as student assignments for project-based learning. So any people here teaching courses or being on receiving ends of courses on audio DSP? Right. So, well, I'll tell my story. When I was a student, before going into any research work, my first contact with signal processing was with a simple thing. I think at the time I was given as assignment to synthesize a musical instrument. And so, even on MATLAB, I wasn't even given MATLAB. I was given a kind of Excel spreadsheet and a board, an embedded DSP board. It was a Motorola DSP 55,000 family. And I spent at the time the best part of 3 months just getting up to speed with that board and the code for being able to do anything, nothing more than read from a fixed table of note values and play a melody. All right, so that's the situation in the bottom slot. So we're teaching a course of assignments. Many years have elapsed since that time. I won't tell you how many. And that's still relevant in academia as a problem. But also, even in the industry, a lot of people need to take ideas and put early on into prototypes before committing to actual products or rewriting the algorithm in C++. So the things that you'll see today are relevant to academia, but also well outside. And well, let me get through this first. So the idea is this: you have a MATLAB algorithm at the beginning. At the end of your workflow, or your life cycle of a development cycle, there will be a product, an embedded one. Say a product, or even a kind of a real-time prototype on a board. This is the step that we're talking about, an early validation. Okay, so being able to listen to what you've put together, to say, you know, how does it sound? What if I change that as I do that? So let me give you a quick idea in MATLAB of what I'm talking about. So first of all, so imagine, the examples that you'll see today are very simple. They are put together so that everybody can understand. No fancy algorithms. The idea will be how do you go from algorithm to something that you can play. So a lot of the things that we'll be using will be simple filters. So let's assume that you are working on a very novel parametric equalizer. Nobody's doing it, right? But everybody knows parametric equalizers. So see that you got let's admit you got in your hands a 3-band parametric equalizer. How fancy. No matter. What would you use MATLAB for? You probably take your algorithm. Can everybody read this? Right? So look at this. ParmEQ filter. Okay, this is line of code. It's calling into a MATLAB function. Let's open this. There will be some code inside here. Okay, it's going that you take in some gains for the 3 bands here. In this case, well, you're fixing the bandwidth and the merit factor. You're designing some filters, and then applying the filters to your input signal. Okay, and then imagine that is a lot more complicated, but you want to know how that sounds. So how would many people deal with that? So how that sounds or how it behaves? Well, set a few gains to pass to the function, get some input from an audio file. You can see up here this MP3 file. It's called funky drums, whatever, stereo. Filter the signal once with a set of gains, -20 in the bass, +20 in the treble, opposite things over here, and then kind of display, for example, power spectral density, so something like that. Okay, so this is it was a stereo input channel. In the middle, you see the original channel, well, the one version with the bass attenuated, the other version with the treble attenuated, and so forth. Okay, very typical thing. It represents a lot more other things that you might want to do, but visualization, MATLAB is great at visualization, offline processing. So you have a whole input, you pass it to something, and you have it as an output. Okay, and you could even go, so very useful. I think we all agree on that. You could also do something like this. You could say, take your input and concatenate it with the 2 outputs and play it out. You know about this, right? Let's get the volume started here. Okay, you missed the first part, which was the original part. No worry, you'll hear it over and over again. So I won't play it again. It will be annoying in a few minutes. So what's going on here? We had some process kind of audio vector. We were able to sound it out. Very useful. Okay, I found it really useful. The trouble is there are so many workflows, and it's difficult to get your hand around about the why. We've done it so many times. We all know why it's important. It's so important not only to be able to reproduce a bit of sound, but to be able to interact with it. So playing in real time. So have audio streams through a system that's normally a box, an embedded processor. Be able to interact with the processor or the box to change the parameters while things happen. To be able to listen and hear, have a human feedback right away on the impact of changes of some parameters, right? What do people do these days? Well, these days, up until recently, they just leave MATLAB to do that. And that's a lot of pain. I've got slides on that, but I won't use them. I think it's intuitive. If you need to go out of MATLAB, and your MATLAB algorithm needs to be translated into something else, typically C, C++, perhaps developed into the plugin for a demo or proof of concept. There's a lot of time that goes into that. The reason why it's a lot of time is because when we own the MATLAB algorithm and it's us writing the code, we're not software engineers. We're not computer scientists. We're engineers. We understand about audio, not typically about C++. We learn about C++ as a tool. Another possibility for many is Maximus P. It still needs some translation from the language that you have into some block diagram. Sometimes you don't have insight into the details. It's a painful process. So what we've been trying to do in the last couple of years is to think about a way, or a couple of ways at least, where you could go from an algorithm to a situation where you could prototype in real time. So let me show you the end result of this session. And this will be just two ways of doing this, and then during the rest, I'll deconstruct both of these things to explain how they work, when they're possible, and what are the limitations. So one possibility is to do things inside MATLAB. So in this case, I have a bit of code that it's sitting behind this thing here, 3-band parametric EQ. Let me kind of show you it for a sec. I've got a tool that I wanted to use here. Let's see if it works. Okay, it does. So this is the bit of code that I'm ooh. No. This is the bit of code that no, not you. Let's see. Not you either. Yes. Okay, 3 lines of code. This is where the algorithm is. There's the algorithm and also some description of what are its variable parameters. And then a line of code to do the visual, this bit here, and a line of code to put together a user interface with some sliders to allow me to change the things of this. This is the only place where I put new stuff, new algorithms, new idea. Again, a 3-band parametric equalizer, functionally the same thing that you see before. The difference is here is that now I'm choosing a file to use as input, same as before, playing it indefinitely, and then just hitting play. Let's make this a bit. Okay. Okay. Don't judge me on the merit of the musical content, okay? Just the workflow. So this is what I was hinting at. A way to get to interact with your algorithm, typically written in MATLAB, as signals flow in and come out. Okay, so that you can change things based on what you hear. So you see, and at the same time you saw that live visualization. The content is no surprise. The 3 bands are raised, the bass first, trebles next, and then the midpoint with a high merit factor, a bit left and right. So this is one way of doing things. Let's abstract this as we are in MATLAB. We got a way of streaming audio in through a sound card, or in this case a file, but I could have just entered through the sound card and exited through the sound card. In this case, I was reading from a file and going out from a sound card. And then doing the processing in MATLAB, running MATLAB code on the audio that's coming in. Okay, this is what was going on. And I'll go through the details of this. But let me show you another possible outcome that we could have, which is this. So let's zoom in a bit. You see that I've got a VST plugin here running in Reaper. The VST plugin is a very simple, I wouldn't call it a beast, it's a very simple thing. 9 parameters so 3 parameters per band and 3 bands, okay? Gain, center frequency, and merit factor times 3. Same thing that I had earlier, except that now it's running as a VST plugin natively inside a host environment, in this case Reaper. And I can do exactly the same thing as before. Oh, except that. Okay, I got it auto-muted. Okay. All right, so what was this? This was generated completely from my MATLAB code. I had my MATLAB code packaged in the right way with the right information in terms of what parameters to expose and to change. And I was able, if doing things correctly, to go from MATLAB code to this plugin with a click of a button virtually. Okay. So the goal of the session is to go into the details of these two workflows and understanding how you do that. How do you go from an idea to a real-time prototype? I hope that meets the expectations based on title and abstract, right? Any questions so far before I go into the details? Good. It means you're patient and you know that I will explain whatever lies behind. So let me get started. So I will, let me go back for the last time to my presentation. And I'll go fast to explain how many slides I spared you. And this is my agenda. So visually, try to decouple these 3 bullet points from the rest. I know this is a lot fancier, but focus on the first 3. So these three topics will explain how it is possible to run in real time in MATLAB and convey a few best practices to make it possible. The first called low latency audio streaming. It's about connecting MATLAB to sound cards and do it in a meaningful way so that you could do effectively real time. It's good that these days, as I say real time, and I'm on a PC, people don't tend to get bothered anymore, right? It's okay. So what you saw was real time, except that I was running in Windows. It's okay. It's a non-real time operating system, but the definition of real time is that I'm able to produce as many samples as I was getting in without introducing different delays along the way, right? So connectivity. Think about connectivity as the first. Efficient programming for audio processing. So I got this question before starting the talk. How is it possible to crack live samples with MATLAB, whereas MATLAB is proverbially slow? You know, I need to live with that perception because I work for the company who makes MATLAB. The fact is, you can use MATLAB MATLAB is a tool. Use it for analysis. It can be slow. Don't pay attention to how you code. Yes, it's small. It's slow. But if you want to make it fast, there are good practices to follow. It can be fast. Just you could be very slow in C++ if you do dumb things. Right? So what is needed specifically for this type of applications? The third is how you structure your code in such a clear way that you don't need a human to understand what's going on and translate it to something that can be operated in a standard way. So if you write a function in MATLAB or a script and then give it to somebody, have them translate it to a plugin, you need to tell them a lot of things. What are the parameters here? Where is the input taken from? What's going on? But if you structure your code in a kind of agreed way, where a human or a machine can go and take the relevant information, then you have enough to automate all of those workflows. So to go from MATLAB to the VST or that interface for all that matters. Once we clarified that, going to the VST, so the second thing you've seen will be very trivial. And then there's the last bullet point, and actually I haven't updated this, which is about closing the loop. Once you have a plugin, which is yours or that of somebody else, what if you wanted to use it in MATLAB for testing or for leveraging something that exists out there and integrate it with what you're doing? We'll see how you can take an existing plugin and make it become a MATLAB object with some properties instead of knobs. Okay. Right. So let's start from the beginning. I don't think I need to show you anything here. Well, I can just show you this so you know what I'm talking about. The reason why I put together this content and I'm spending some time being out and about, talking about these topics, is because in March 2016, so about a year and a half ago, we released that new toolbox. That's now part of the site license here at York. So any faculty or students can have it and use it at home or here. By the way, how many people are local here? Can you, just to give me an idea, can you raise your hand? Anybody from outside? I heard that some people come from Huddersfield. Is that the case? No?
I think there was one person who was going to be coming, but they texted me so they've not been able to.
All right, okay.
So, but they were
One emailed me as well. Okay, fine. So I take anybody else from anywhere else?
Yeah, we're from Leeds. There's a few of us from Leeds.
Okay, well, thank you for coming. Right, so anyway, I'm not sure what happens at least with this. Hopefully, either you have it or you have it or you will have it soon. There are commercial reasons sometimes where it's difficult to add it, but I'm not in charge of all that things. So hopefully you'll get it soon as well. So it's a new toolbox. So it didn't exist. You weren't able to do these things. So if you want to be able to do these things, you need to make sure that when you have MATLAB installed, that is part of what you're using. And inside that toolbox, there's these groups of things. So like any respectable toolbox, there are a few algorithms in there. Don't expect that that's going to make your job, hugely easier. There's trivial stuff in there, the crossover filters, the equalizer, the basic things that either are parts of what you're doing or give you a way to, compare you against something that's well established. The connectivity to standard hardware, so low latency drivers like Azure Cordio or ALSA, depending on the OS, as well as the other standard one, typically on Windows. The ability to do live tuning. I haven't shown it, and I won't show you today because I travel by train. I didn't take much, but think about also connecting MATLAB to MIDI controllers so that the tunability doesn't happen with a mouse, but with an actual physical knob if you need to do so. And then the workflows to the plugins hosts. So the ability to generate plugins, VST plugins, and then the ability to host plugins in MATLAB. Okay, so all of this comes with me in this box. That said, I'll go back to MATLAB and I'll try to stick there as much as possible. And so let's try it. So last time I gave this talk, it was I think 6 months ago or so. So I sometimes I'll skip some steps and I get ahead of myself. When I showed that plugin, that was generated using basically this line of code. That's the name of the file that I was working on with the actual MATLAB doing the equalization. And this is the command, the built-in command, generate audio plugin with the name. What you get out in Windows is a .dll that, if open in a host environment, gives you that plugin. We'll see it in detail in not long. So we are at a starting point. The first thing that we set as objective is understand how to do real-time in MATLAB. Okay, and the first part of that was how to connect to audio hardware. So I deconstructed that problem to bring it to a bit of code that's as simple as possible. So you've seen that as I was going through my script, I click on portions of this script and it lights up, right? I'm executing a section of code at a time. I hope most of you will be familiar with this. My code is subdivided with these double % comments. If you put a double % comment, MATLAB put a kind of an ideal division here. It means that you can execute this all in one go, or if you put your mouse here and hit on that button, run section, you can run only this bit of code. Okay, it helps you going through subsequent steps and showing what you have. Okay, so let me execute this bit of code that goes from up here, you see light yellow, down to here. I'll execute it first by running this. It's a high-pass filter through the same bit of, okay. Because it's high-pass filter, it's also low, because a lot of the content, a lot of the energy was at low frequencies. You can see the original signal in yellow, the filtered out in bluish, and the spectrum is just there to show you that it's happening, that as it's being read. It didn't happen earlier. I'm just playing it out. Okay. So what's behind this? What is it that is making this possible? The main thing to look at here is this while loop. So what goes on here? You probably know what tick and talk is a way to measure time in MATLAB. So this is saying up until I reach 60 seconds, or that spectrum is up and running. Now I closed and it stopped. Keep executing these things. And what goes on here is that I read audio from my card. This is a MATLAB matrix. As many columns as number of channels, as many rows as number of samples per block that I read. I filter X, and I run it back. Well, in this case, actually, I was reading from a file, but it's the same concept. So, and then visualize input and output. So as simple as this. You don't need anything else. I can leave now. There's more to say, but in terms of using real-time streaming, this was neat. Now, I think what's interesting lies behind this. When I first, probably in my first 6 months working with MATLAB and doing DSP, I definitely tried to do this at the time. It was a few years ago. It just didn't work. There have always existed functions to get audio from sound card and write to sound card in MATLAB, right? So those are functions that come with the basic MATLAB package. What those functions do, if you type write, for example, they take your audio, the digital audio, so vectors, and then they see, okay, where is it that I need to play this? Okay, the name of the sound card is this. Let's try and look for the sound card. Identify the driver. Good morning, driver. Let's allocate some buffers in memory to exchange the data. Buffers allocated, and then starting passing the data. Pass the data, pass again the data. Once the file is finished, okay, done. Goodbye buffer, goodbye driver. nice seeing you, get out of the function, return control to the program, and anything that's inside that function has been forgotten, has gone out of scope. And so compared to the time that it took to pass the values, the samples to the driver, there was a huge amount of overhead to allocate the buffer, the memory buffer, and to identify the drivers, to do the initial checks. The reason why this is working is because when you see that outrider now is something a bit smarter than you would imagine. It's not a function, despite its looks, but it's an object of that class out there. So you can see it's called audio device driver. It takes, in that case, just one input, which is the sample rate. It's going with all the default options for the others. What basically that is doing is saying, OK, create an object that can exchange data with my sound card. And once you create it, let it stick there. You see it's created outside of the loop. Once it's created, I only need to pass it samples. It will remember who's the driver that I'm talking to. It will remember where's the memory buffers that where I need to stick the sample. So when I actually call it inside the loop, what it needs to do is to just handle the samples to the driver, typically pass a pointer. So it's super efficient, and what it needs to do is really trivial, provided it does it well. So it does it in a way that when I pass the audio that I need to write, nothing is forgotten. Okay, and this is possible through using things that are nowadays very popular and adopted in software, called classes and object instance of classes. You'll see this concept recurring. It's quite important for a lot of the efficiency considerations that we'll talk about. Okay, I'll stop there. The other important thing here is, would be reading. In this case, I'm reading from file, but that I could have read just as simply from hardware, right? So let's take a look at the mechanics. So, because whenever you take a piece of software and you need to connect it to hardware, it's never easy. So I want to show what it takes. So in this case, what if I wanted to read instead of from a file from my hardware? So you can't see it. I'm a bit hidden here behind this wooden wall. I've got a simple sound card here. I'll try to raise it. It's 100 quid kind of hardware from Steinberg, a 2-channel in and out. The reason why I go around with this is because it's got reasonably decent ASIO drivers, so I can talk about a few topics. Now, let's say that I want to read audio from this piece of hardware. All I need to do is say inReader equals audio device reader. Okay, and then I'm returned with a few properties. So I've created an instance of that class. This is my object. And you can see that I've got drivers and device here. So by default, this is direct sound, but I can say in reader equals open quote dot driver equals, and I got the choice, hit enter using ASIO. So ASIO is set. And if I do the same thing, but say device, I got the choice of all ASIO compatible devices installed, so I can go to my card down here. Okay, Yamaha Steinberg USB ASIO, and then I can set the number of channels, how many samples per frame I want to read, the sample rate, and so forth. Once I have it set it up like that, I can right away do live acquisition like that. So again, a while loop for 20 seconds, just read and plot what you read. So let me do something simple here. And actually I had a few things connected not in the right way. So let me connect everything. So make sure that you hear everything. Okay, so now I'll use this to get into my phone or out of my phone, where I have a simple application that I loaded some time ago to generate tones. It's called Signal Gen, just whatever. Okay, so I got a few controls in here. Okay, so I'm set now in low frequency. I will take gain to the maximum, and I'll go from 80 Hz onwards for 20 seconds. So let me execute this. Okay. Up with frequency, up again. Right. So for example, if you had to set up a measurement, a live measurement using MATLAB, you could take a pretty high-end sound card with a good SNR and THD specs, put in your bench, and use MATLAB to stream audio in and to do live measurements just like that. You don't need anything more. It's quite simple, right? If you now take this, make it a slight bit more complicated, and you've got the whole DSP box kind of idea. So this here is for 30 seconds up until the plot is on. I read, I do whatever processing I want. In this case, I don't do anything at all. And then I write back. And let's do it again. Let's start again from a low frequency and go up. And now we should hear it because I'm monitoring through Outrider. It was the same as before, what I'm putting in. So. And down. Great. All right. So that's the basics. That's the mechanics, though. So the mechanics is this. Let's review it a bit. Use the right things to connect, things that are efficient and can afford to be running the loop because they don't forget about all the things that take a lot of time to initialize and dismantle. And know what properties you need to set, and basically there's no more to say. Now, besides the mechanics, you probably, if you have ever done this or tried or thought about this, you probably will have a number of questions. You probably have it in your head, but I can anticipate you, which would be, how many things you can run in here, or what kind of latency can you get? I guess the latency is pretty important, tends to be pretty important. So let me talk about that. That we can connect and acquire and play back, may not be a big deal. Can we do it quickly enough so that we can actually be real time? That means that we don't change something and that something happens in 2 seconds because it takes a huge time to process the data. You saw that I was using ASIO drivers. ASIO drivers are de facto standard in professional use of consumer audio interfaces because they allow a few things. They allow low latency. They also allow to do synchronous multi-channel acquisition because most vendors only bother to enable those with ASIO drivers. So that was the kind of driver that I was using. Now the question is, with that kind of driver, how down can you go in latency? You saw that, for example, when let me make it big. When I created, I wanted to do this time. When I created that object, I didn't touch this property called samples per frame. So what we call a frame, other software environments calls a block. I think that's it, pretty much. You have the same parameters in any DAW, digital audio workstation, or a VST host. That means how many samples does the algorithm see in one go, or how many samples do I collect from the sound card in one go? In an ideal, that doesn't happen very often, but in an ideal embedded real-time environment, you would be able to have one sample in, do something with it, and one sample out. That's how we study all DSP algorithms. Like when we write down the equation of the convolution, we write xn, and then as xn is available, we have yn. And in theory, we could think that we can always pass a sample in and have a sample out. in theory, in practice, even real-time systems work on buffers. And here, where we're on Windows, we cannot but work on buffers or blocks or frames, okay? One sample at a time doesn't work. If you were able to work on one sample at a time, you would say that you have zero latency between input and output. The only latency that you introduce will be algorithmic, for example, the group delay of the filter that you're using, right? In this case, you don't. Why can we not? Well, we are in a non-real-time OS, so that means that we cannot place our money on that when a new sample is available, we'll have deterministically the time to process and return it back. The operating system runs all sorts of things, so we need to be wise in the way we use the resource. We acquire a buffer of samples at a time, process it. We'll have quite some time before it's time to return those samples processed to the output, equal to the delay of those samples. And so we can use that time to do our computation and also wait before we pass the output samples if the operating system is running some other task. Okay. So that's why all systems that do real-time audio on a non-real-time operating system use buffered options. And that buffer size determines your latency, because that is the size that you need to. That is the time you need to wait before you return it to the output. It's actually a bit more complicated because the drivers also have buffers. So when you use, instead of guessing how much latency you have, that's how it works. When you use an ASIO drivers, you have a utility. In this case, this is what I have right now. That allows you to set how many samples do you want the driver to buffer for you at a time. In this case, you can see that I was at 128 for the driver, okay? But I could go, for a lot of samples or low samples. So the lower the number of samples, the lower the latency. And a given driver will tell you what's their built-in latency, and this is due to the way the driver works, not any software like MATLAB. Okay, so see this number 6.78 on the input pipeline and 7.7 in the output pipeline, so about 14 milliseconds. Now, if in MATLAB we can say that we want to also acquire 1 to 8 samples at a time, and if we do that, we should be able to honor that latency. So that the latency is imposed by the driver, not by MATLAB, in other words. So let me do a little experiment to prove it. The next cell of code that I have here is a bit of code that's measuring an impulse response. You can see that I am setting the frame length to 1 to 8. Sample rate is the same that we had there, and so what I'm doing now is I'm going to connect input to output, left channel to left channel. I'm going to use a pretty antiquated method, an old one, MLS, maximum length sequences, not used very much anymore, but very easy to code. We might hear a bit out of the loudspeakers. Let me run this. No, likely no, it's not going through the right channel as well, because the left channel is now disconnected from the AV system. So this is what I'm measuring, not a perfect delta. So I had a wire, so I wasn't expecting to measure any fancy impulse response. I had something very similar to a delta, a bit distorted because of the filters and the little high pass and low pass of that system, and it's about 14 milliseconds. Okay, so that's the actual latency that we had in our system, the input-output latency. I'm going from MATLAB through the output of the sound card, that's the output pipeline, and coming back from the input, that's the input pipeline. What latency is between my sequence in output and my sequence read in input. That's the number. And if we take a read here, it's telling me that that the latency was about 14 milliseconds. And if I have those numbers in my MATLAB command history. So if I sum input and output, that's what I get, a number that's really close to this. I measured something that couldn't be smaller than this. There's a measurement error here, but that's exactly the same number. So I can go as low as the sound card and its driver allows me. So this is not a good. I like it. It's a simple sound card. It's not the top of the range. If you use something like an RME card, you can go as low as about 5 milliseconds. We measured 3 point something on a Mac with Core Audio. So that's what we're talking about. So how do you do that? You get a buffer to as low, a buffer size as low as you can up until you don't drop any audio. You could put theoretically up to 32 samples or 16 if the driver allows you, but what you'll see is that you'll be fighting against Windows or Mac OS X. So that means that you're not keeping up with real time anymore because you're losing buffers, you're dropping buffer once in a while. But until you don't drop, that's your latency. So go as low as you can without dropping. When we measure it, we like to get good numbers. So when I tell you 3 milliseconds or 5 milliseconds, the kind of experiment run there was without doing anything. So it's a wire. Y equals X. So your code was not impinging on the whole computational load of the system. With the more you have to execute, the less you'll be able to have. The greater will be the latency. Yeah, the smaller your leeway. Right? Does this make sense? So we cover the mechanics of connecting, the latency along with it. There's a third question that comes pretty natural in this context. That was my probably second item on the agenda. That is, how do I make sure that, how many things can I run by doing this? Can I just run a kind of a high-pass filter or a 3-band parametric equalizer? Is that all I can do? Or can I get more complicated? And how much more complicated can I get before I start dropping samples regardless of latency, right? So in other words, I showed you something happening in real time, but how complex can that something be? So let's try to answer that. And I'll take a few tours before answering that. And you'll hear the answer in about 15 minutes. But I wanted to draw your attention to, first of all, go back to that initial examples and understanding what was I doing here when I was doing that high-pass filtering that I showed you before. Let me execute this again. Only right channel, right? The other is wired up. So high pass, what was I doing here? I was reading from a file, equally well I could have read from the sound card, doing something with my input, going through that function, then writing back, right? Now we focused on this and this. Let's focus on this. How complicated can this be, right? So the way this is done here is through a regular MATLAB function like the ones that you would write yourselves. So let's zoom in a bit. Okay, so let's take a look at this function. So you enter right there. You see as any function, you've got a number of inputs and a number of outputs. The signal that comes in is that in matrix. Okay. Try to keep in mind this mental model. Every channel, typically, for the convention that we use, goes on a column. So as many columns as the number of channels, and as many rows as the block size. Okay, the number of samples per frame. And then there are a number of parameters. So in this case, I had a parameter called cutoff frequency, which is a reasonable thing that a high-pass filter may want to expose. Okay, and then I use that cutoff frequency here to compute numerator and denominator of a biquad filter. Okay, and then I use that numerator and denominator in this ever popular filter function. Hands raised who hasn't used the filter function in MATLAB ever. Okay, I take it's not shyness, it's that all of you have used it, right? Now, there are a number of things that I don't like about this function. And the reason that I don't like them is that they don't, in first place, they don't make it as efficient as possible, and also they make it difficult to use, understand, and so forth. So let's talk about efficiency first. What happens here? Imagine, like in our case, I had a static high-pass filter. Cutoff frequency didn't change. What was happening here? Every time that I had new audio, function is called, a new input certainly. As much as this function knows new cutoff frequency. So I go here, compute the coefficients, even though I had them already. But OK, compute it again, and then use the coefficients here. So I'm computing this code every time, even if I don't need to compute it every time. I mean, I only need to compute that when the cutoff frequency changes, right? I don't need to compute it every time I enter a function. So what could I have done? I could have compute these outside of my function, maybe, only when the cutoff frequency changed, and then pass the coefficients in, which would have meant basically using the filter function. So I guess efficiency is fighting against the ability to abstract complexity away. If I want to give something simple to people, which is only cutoff frequency, then I need to be inefficient here, in a way. So let me go on this track also. Take a look at all those variables that I'm passing in. Look at the last one, state. What's that? Take a moment to look and try to figure out if you can understand what that is and why it's important to pass it through the function interface. Look at it. I'm also having it as an output there. You normally don't need to do this in MATLAB, right? So think about how we use the filter function normally, how you use it. I bet that when you use the filter function, you only use it like this. OK, so BAX, and then you have Y here, and no brackets, right? So how does that work? It surprised me a lot, I remember, the first time that I saw this. When you do convolution, you need to think, OK, L long sequence, then M long vector. And the output is L plus M minus 1. But instead, the filter, you pass it a vector, and you pass M, and you get M. Awesome. You don't need to trim or do anything. It just does the simple thing. The filter command assumes that internally the filter is virgin. The FIFO is full of zeros. The input starts to come. The initial part of the response will have a transient, and then the FIFO will be filled up. And then when you have enough samples in the output, it will just stop processing. Okay. What happens if you run that same approach on subsequent buffers of signals? Every time you'd have an empty FIFO in the FIR filter, and you'll be starting from scratch. The filter command will say, OK, hello, let's filter you. And I assume that the state's 0, right? There was no history before you. Except that when we stream audio, we pass a buffer at a time. So actually, there is history. So if we are processing buffer number n, the filter needs to know about what happened at buffer n minus 1, because that changed its states. If we didn't take it into account, we have a monstrous number of clips and discontinuities and transient that wouldn't need to be. So the filter needs to remember about the states. So if we use that filter function, it means the state needs to be an input, because it actually contains non-zero information from the past. It's basically saying the filter, pretend that you were the same that you were last time, just ahead in time. And then it needs to return the modified one. And this needs to be kept safe. Because it needs to be kept safe, it needs to be passed out of the function. Because when you leave this function, if you didn't pass it out, it will be forgotten, out of scope, go in the bin. Okay? So it needs to be maintained by the outside world. Am I making any sense? So that's terrible, because the outside world now needs to know an awful lot about how I work. Imagine, depending on the order of this filter, is it a kind of a single, two-order IIR, second, fourth order, two in cascade? How many? Would you be able to tell me what is the state of a filter like that? It depends on the number of cells. It depends on the number of on the structure. The SOS, form 1 would have 4 for channels. The form 2 will have only 2. Pretty horrible. Okay, so and that needs to be known from the user, because it needs to initialize this to 0 the first time that it's calling this. So why don't I like this function? Because it can be inefficient, and because the way it exposes functionality to the world, it's awful, and as a result of using it in real time on stream signal. Normally, you don't have this type of problem in MATLAB,
Only when you go to C or in a real-time language, you need to ask these questions. But now you need to think about those things. So let me propose you an alternative way of doing the same thing in a more efficient, with a more efficient approach. And no need to for a ta-da, but this is something different. There's no function up there. You can see there was this says is class def. It's the definition of a class in MATLAB. Anybody's has come across this in the past? Can you show me how many? Okay. It's unsurprisingly, it's a minority of you. And to be honest, a lot of time when I give this or similar talks, I see a lot of faces going a bit gray and thinking, come on, you know, there's a reason why I'm using MATLAB, because I like simple things. I like to think about the engineering side of things. I'm not a computer scientist. I'm not, you know. And the truth is, you know, you're right. I think that there's a benefit to staying simple in MATLAB, but where you hit some point where you want the benefits from advanced maneuvers, then you can do a bit more. And the good news is that writing classes in MATLAB is way simpler than any other language like Java or C++. So this is how it works. Well, I guess we have that class def at the beginning. Try to ignore it. That's not pretty important. It's just a matter of syntax. Now, the one thing important to see is that we have groups of things. So we have groups of things called properties, and then we have groups of things called methods. Properties are just variables. And if you say equals something, that's their default value. And functions are what people call also methods. There when talking about object-oriented programming. So let's, one thing at a time. So first thing, up here, this is telling me that this class has a public property. It's public is the default settings. We only say properties. It's called cutoff. What that means is that so this class is called high pass. So if one goes in MATLAB and says, and says filter equals high pass, this is what they will see. So they will see that there's something to change, that they can change. There's a cutoff. Similarly, have you ever worked with MATLAB structures, collections of values? It works in exactly the same way. So you could say filter dot cutoff equals 20, and it will be set to 20. It gets users of your code a way to immediately identify what they can change and what they would want to give up understanding. The other thing that we have here is that we have this function here called process. And the way this will work, if you can see the common window up here, is that one could say filter dot process X. Okay, this will be a way to use this, or even this, more popular, process filter X, where the first argument after process is the name of the object, and this will be its method. So look what this does. This does exactly what we need to do at real time. At real time, you know, we may not need to change any parameter. We need to accept an input, here, and return an output. Okay. Now, what this is doing with that input is exactly what we had in our function. So it's putting it as an input. So filter BAX, think about this X. But now, B and A, they're not computed. They're used. See this obj.b and obj.a? These are values of the numerators and the denominators that were stored in my object whenever they needed to be computed. See this property group up there? Those are the properties that are the data. That's the data that stays with the object, but is not visible to the user. So whenever I change the gain, and I'll show, so the cutoff frequency, I'll show you in a second, those values get updated and remembered. So they're available to anybody, any function in this object to be used. So here I only had to say obj.b, and I go and grab the value of the numerator on A, and then I can use them. When I'm finished, I return the output, and I store the updated state also here, and that belongs to me. I know how to initialize it and how to use it. So let's see a bit more of this thing. So we have this cutoff. When I change the cutoff frequency from outside, so doing that, cutoff equals 20 as I did, what happens is that I can say that something happens whenever that value is changed from the outside. I do it like this. I create a function that begins with set dot and continues with the name of the property. And this is saying whenever somebody says filter dot cutoff equals 20, I take that 20, which is the value passed here, I assigned it to my value, to my property, so that people see it. And then I do whatever I need to do. In this case, I compute the coefficients of my filter. And once I compute them, I store the values in my properties. So they are there and they can be consumed. Okay? So I separate the tasks of updating the coefficients and running real time. Running does only what I need. I took away the complexity from the usage in that I expose what can be changed, whereas before I had cutoff, input, state, all in a list of input variables. Who knows what is what from the outside? I need to go and read and go through the code to understand. And my process method now is simple. It can be understood. If I make a statement and I say every time that I write an audio processing algorithm, I will always write a process function and it will always look at the same way. It will take one input and it will return one output. That input will be my input matrix, as many channels and sample per block, and the output will be the same. It's an agreement. It's got the power of an agreement. And in all what's in this toolbox, any bit of functionality will work this way. Okay? So if we follow this practice, then we can. Let me see. Okay. If we follow the practice, then we have a way of being efficient, and also exposing the right interface to users. Now, before I let me show you this bit of code. Now, so if we have those, if we can change those things at runtime. So if we could say filter.cutoff equals 20. Look how the same code that you've seen before would look for if I use this construct. See that while loop I was reading from device or file, writing from device or file, and in the middle I used to have a function. Remember here, I used to have this function here. Okay. Now we have this use of that object that I built. So right here I create the object outside of the loop. Okay. This stays in scope, it's not forgotten. Anything about it's kept in scope. And when it's time to process the input, I simply pass the input signal to that filter and I return an output using the process method. The filter now is also known to my MATLAB code here. So here I'm also passing it to this function that creates a simple user interface. And I'm saying that I want to change the cutoff frequency. So let's execute it. Oops. Okay. So magic revealed, I would say, right? This not. When I showed you that example of a UI in MATLAB, was not. Now you know all about it, pretty much. You know that behind the scenes it had a loop like that. It didn't do anything else that take my algorithm that was well structured, understand whatever was changeable, and do it. Except that it didn't do only that. So let me show you. Let me do this again. Let me turn the volume down. See this UI? It's allowing me to change the cutoff frequency from 100 to 2000. Okay? And these values I specified there. Can you see that? 100 to 2000. In general, that's something that you want to know. When you have an object like that, and one tells you that you can tune a property called cutoff. In order to be able to automatically paint an interface, like I did at the very beginning, where I had all my 9 parameters nicely going from one value to the other with the right scale, linear logarithmic, I need to say this. So that cutoff frequency is a frequency. So typically it wouldn't go lower than 20, but hey, perhaps yes, why not? More than 20K? Yeah, probably not, but anytime, but maybe the range is smaller. And how to go from the lower to the higher? I would suggest, a log scale, probably. But that doesn't apply to any parameters. Some, the dB parameters would, very likely go on a linear scale. So, can we say, is there something more that we need to say? We need to tell MATLAB or any automated mechanism that transform this code into something more usable to say how the parameters change? This is right inside here. There's a block of code here that I had hidden as I had opened this. See, there's the plus sign. All the others are expanded. Honestly, this was less honest. I'm going to hide this. This is a bit of horrible code, the type of code that you typically copy and paste and modify a few bits. But let me guide you through this. This is saying basically that we want this class to have a recognizable interface for every one of my properties that I want to paint a control for. I say, in this case, I want to paint a control for the cutoff frequency here. I want to display it in some way. And see this mapping thing? I want it to be logarithmic from 20 to 2000. As I say that, I solve the whole puzzle. I can go from a bit of code to something that automatically gives me a control and hooks in an input of my choice to an output of my choice. How can I do that? Because process always looks like the same. If we have a process method that we guarantee that works in that way, just takes a matrix's input and a matrix's output, problem solved. You give me the code, I hook it up to inputs and outputs of your choice, and I give you a set of controls for you to control it. And so if I take this code, this high pass code, and give it to that command that you saw before, audio test bench, what this gives me is this, from 20 to 2000, okay, with the right scale. I'm in the middle here, and I'm 200. Okay, I'm not about 1000. And now I can choose from whatever input here, whatever output. So let's go and pick my input. Funky drums. And okay. And and I could choose how many samples per audio frame. Doesn't matter. I could say 64 sample for it matters. Then I'll just pass a 64 sample deep matrix to the function. The function just needs to be able to deal with it. And play. Okay. So let's think back. That now we covered how do you connect to hardware, and what expectations do you have on latency. We covered how to package your algorithm in a way that is efficient. I haven't covered all the efficiency problems in MATLAB. There are training courses that people pay for to understand how to write efficient MATLAB code. All the rest of considerations for efficiency hold true. So could you name a few good practices in MATLAB for efficiency that you've been bombarded with at perhaps some courses?
Avoid using loops.
Say it again?
Avoid using
Avoid using loops is one, right?
Pre-allocation.
Pre-allocation, okay, great. These are the two most popular that I would have. So what do those mean for the others? So avoid for loops is also sometimes called vectorization. It basically states if what you can do can be done with a matrix operation, just go for the matrix operation instead of writing the for loops explicitly. Why? Well, because first of all, because MATLAB is interpreted, so interpreting one operation is just one interpretation, whereas interpreting a full loop is whatever the number of instructions. But more importantly, because MATLAB can use optimized algebra libraries behind the scenes under the hood. So if you pass a matrix, it will call the multi-threaded operations in the BLAS library, and it would be just more efficient. It will be more efficient than your own code written by head. So that still holds true. Pre-allocation was another one. And that sounds like that. So that has been very, you might not know, but there's been a lot of work into not forcing people to do that. So it used to be that if you said A equals 1 in MATLAB, that would create an array type 1 by 1 and put 1 in that position. And then you said A equals 2. MATLAB would be forced to put the two, A1 equals 2, the 2 and the 1 in a consecutive place in memory. That's the requirement. Otherwise, it wouldn't be able to call those BLAS libraries that need arrays to be consecutive in memory. So it couldn't put the 2 somewhere else. It could need to make sure that the 2 and the 1s were together. So we'll do this. We'll say, you know what? Never mind. I create a new one. We'll create allocate a new bit of memory with 2 double precision floating points. Copy the 1 from the old position to the new, write the 2 into the new position, and get rid of the old one. Okay, which is okay. Think about larger and larger. Growing by 1, a vector of 1,000 components. It will be hugely expensive. Now, the MATLAB looks forward to your code these days and try to spot those murky things and do reverse engineering and pre-allocate itself without telling you. But still, it has an impact. So that guideline was, if you know that you need to create a 124 long vector, don't create it in the loop. Don't grow it. Just do pre-allocate it. Do zeros, for example, 1 by 24, and then fill in and say x1 equals a value and so forth. Okay. So, and there are more things like that. So all of those good practices still apply, but for real-time audio, there's separation of concern to do only the things that need to be done at runtime and do the other things either at initialization or at tuning time. That's really important. So efficiency, connectivity, but I haven't, and also how to organize your code to expose the right parameters so that I can automate the creation of interface and so forth. So all that I've covered. What I haven't told you yet is how many things can you do. So let's just answer that question, which is a very genuine and normal question. So let's look at this portion of code. I'm calling this function, which is calling a number of FIR filters serially. So it's reading 496 samples from a file per block. So long latency, but best possibility of not being dropped or not being interrupted by the system. Using a sample rate of 44 kilohertz and running 150 FIR filters of half a K taps each. Okay, the game is, let's do this, and inside here profile how long I take for every new block of audio to run 150 FIR filters serially, and see if I can manage to do that, and how much time is left or how much time is not left. So I'll execute this, just a few seconds, and then it will return kind of a graphical report of what's happened. And I'll need to go through the report. It's not probably apparent to all. The other thing that I should have said is, and I'll say in a minute, it's what are the requirements? Okay, so that's my report. Let's make it a bit bigger. So 2 parts of this. Let's focus on this first. So this was running an audio loop for 200 times. So 200 times I acquired 4K samples. Okay, so that was the duration of our acquisitions. For every acquisition of block, again, I run 150 FIR filters, okay, on that block and kept the state in memory. And this is the time that it took. It's the dot on this line. So every subsequent dot is a time measurement at a number at a block in time, okay? So theoretically, this should always take the same time, but because we're running on Windows, sometimes we measure more time because something is happening as we compute, so we're interrupted and so forth. But overall, it takes us about, this is in seconds, so 50 milliseconds. So this is how much it take. This is the headroom that I had, okay? So I had this, so headroom. This is the time capacity that I had to run those computations. So I was well within the capacity here. And if I plotted this on, if I wanted to do some stats on this, this would be the distribution, and this on this curve, this is the time. So I was well below the tolerance line. And as a matter of fact, if I reverse the problem and I take the median value of this number to say on average how much does it take to compute that 150 FR filters, and I compare it to this, I had an output in the command line that told me in this case I could have run up to 288 separate half a K type FIR filters. So that's quite a bit of computations. It might not be enough for all problems that you have in hand, especially advanced spatial audio things, but it can get you pretty far. Now, let me explain a bit what I was doing here. If you had to write your own FIR filters using for loops, so for N, for K, which is my tap number, no, which is my sample number around the convolution, I wouldn't have gone that far. Actually, I could have run probably one or a few FIR filters. The reason why these are taking so little time is because, like many other things in MATLAB, they've been written for efficiency. So yes, if you write your own filter, it is inefficient for the reason that we said before. But if you are able to pass a whole block to a function that's been written in C++, leveraging Intel performance primitives and all sort of things, then we will just take the bare amount of time necessary. Okay, and these are serial FIR filters in the time domain. No frequency domain, no partitioning. But I was talking to Gavin earlier on. You could try the same exercise with. This is good for short filters, so 120, and it's the best possible thing you can do. For a longer filter, this wouldn't be the right thing, but you want to use a new type of filter that we released, called partitioned frequency domain, which is called DSP. So this thing that I was running inside here, they're called DSP.FIR filter. That would be DSP.frequency domain FIR filter, something like that. It's a new thing. It's got the option for partitioning, which is, again, good for long impulse responses. So this is just to give you a ballpark expectation of things that are possible, as was the metric on latency, just to set the market somewhere meaningful. Questions? Right. So let's get back to our bit of code. So we were able to write a bit of code. We saw that because that bit of code is structured in a standard way, we could paint a user interface. And just to satisfy our curiosity, let me open that 3-band parametric equalizer that I used at the very beginning to show you that this was as well a class. Okay, it had in this case 9 properties: 3 center frequency, 3 quality factors, 3 peak gains. It was just more complicated to guide you through visually, but it was exactly the same principle as before. It was slightly more complicated. It had this collection of awful parameter settings to instruct any hosting mechanism on how you want to change your parameters. So take a look at this. Again, every line of this is one of those faders. So mapping linear for -20 to 20. This is the gain in dB. Fine. This is log, linear, and so forth. A variation of things. And then, as it was in our case, it had some algorithmic code that, in this case, was using some built-in functions to design biquad parametric Q, and that was only triggered whenever the parameters were changed. Okay, so the philosophy was the same, but it was just slightly more complicated. Now, so we learned all of these things, and what is missing to go, instead of paint a MATLAB interface, to generate a plugin? I guess nothing in terms of what you need to do. You need to do exactly the same thing. You need to structure your algorithm in the right way so it is legible, intelligible, understandable by MATLAB, and we can then do all the manipulation of the case based on what you want to do. The little bit of technology that we use to generate the plugins is that we take that code that you write, we translate it into C++ automatically using some technology that's been around for a while within our products. For a number of years now, you were able to take some MATLAB code and generate C++, C if you wanted to. There was a kind of similar to Toolbox, an add-on product called MATLAB Coder. In this case, Audio System Toolbox used the same technology, just doesn't charge for it because it doesn't give you the source code, it only gives you the library. So it's easier to get that running. Traditionally for university, people didn't used to have those tools. But the technology is that. So that code is interpreted, parsed, understood, converted into C++. Obviously, by running awful MATLAB code, or not giving enough thought, regardless, the C++ could be awfully inefficient. So don't expect that this will right away will give you the best performance out of the box. There's still some intelligence needed to get a good bit of C++. It's an automated mechanism, but doing good things will do, avoiding doing stupid things, such as computing things where you don't need to be computing them, will help you get a good C++. And then what we do is that, normally I say we take generally coded, hook it with a VST API, and then compile it all together. As a matter of fact, we use also some tools developed by somebody who was here, Ollie Larkin. It's a tool that's available to everybody. It's called Whittle OL. It's a bit of it's a middle layer that allows to then produce plugins. In one go, it can produce plugins that can run on any platform, for example, and it takes away a bit of the onus. So we basically reuse existing solutions out there to deliver a library that's kind of pretty slim, efficient, and concise in size. So what goes on? You take your MATLAB code, translate it again into C++, hook it up, compile it, and deliver the library. Last problem that could occur is that if you do something stupid in MATLAB and execute your code, what happens? If there's a bug in your code.
MATLAB crashes.
No. Wrong. Never. No, it's not true.
I've managed to do some quite interesting things with my max functions in the past. So.
Max functions, okay. I won't translate for everybody. Perhaps not everybody's familiar with max function. Max function has to do with C. Normally, when you are in MATLAB, whenever something goes wrong, unless there's something very wrong that we're not aware of, and MATLAB crashes, MATLAB shouldn't crash. MATLAB should look ding, red error in the command line, and you go like that. You go back to your code, you put a breakpoint, and very easily you get to understand what's wrong. Now, what happens if you do something like that? Then you generate C++, and you got a DLL, and you host it in your DAW, and then you run it. Then you do serious harm. You can blue screen your machine, right? So we thought about, in the past, we thought about producing, before releasing this product, we thought, okay, you know what, we should be really serious, as always, but even more about documentation. We should encourage people to do rigorous unit testing of their code to make sure that there are no errors. And so how many people here know what unit testing is? Okay, is that 8%? So we worked out that it wasn't fair. MATLAB has a unit testing infrastructure. MATLAB is used by professional programmers to do serious stuff, but it wouldn't be fair to put that onus on the average DSP, audio DSP programmer. So we did something ourselves. We put together an infrastructure. Let me put up a bit of code here. So 281 generate audio plugin is the golden nugget of what you need to get an audio plugin, a VST plugin from your code. So in this case, high pass was our code down there at the end. We can run generate audio plugin on high pass, and boom, you have the DLL. Unless you've done something weird. By the way, not 100% of the MATLAB code can be translated into C++. If you use a MATLAB construct that's not supported, it will throw an error. So it will. I don't want to sell you things as they are not. So this has some a few limitations, and there are fewer and fewer as time passes, but still there. Anyway, if all works well, you got your plugin. By adding this out there and putting it into a folder, you generate it and put it directly somewhere else. So, for example, it's on the path of your VST host, and it's immediately recognized, and so forth. But before doing that, you want to do this as well. Validate audio plugin on your code. And what this will do, it will take your code, shake it, hammer it. It will input input audio buffers of different channels, different length. It will try to change parameters and see what monitor the other parameters to see nothing weird happens, and so forth. It will stress test using a number of standard approaches. And in 95% of cases, if your code passes that test, it should be safe to run in any digital audio workstation or host environment. So let's execute this. So I go here again, run this section. Okay, it says it's checking the class. It checks it in two ways actually. Oh, okay. Error using generate could not open this thing for output. Permission denied. You know why? Because I had Reaper open here. So let me close it and yes. And we basically were trying to overwrite a DLL that was in use, and Windows denied access. So instead, let's try again. So now first it took my MATLAB code and it stress test as MATLAB. Then it generated a MEX file. Out of that MEX file is just a way of having C code running in MATLAB within MATLAB. Don't worry about that if you never heard about that. But it stresses it as C++, as C, and then eventually it generated the plugin. So it was ready to generate a plugin. That was the output returned by this, and then done generating VST plugin is just my display here after this is finished. So now this has been generated. If I go to this folder, I can see my high pass. Okay, 1522, 1523, generated now. And now I can go to Reaper. Let me open it into, let me open it in a bit of another way than hitting on the button. I'll explain in a minute why. So let me go back. And what can I, no, I need to go here. I'll open a, go here. I'll open a command window. Now it's called PowerShell. Let's launch. Okay, now I'm in Reaper. I've got this very original track here. Let me remove this and remove this. And no effects loaded. I've got, okay. All right, so I've got something here. And now I can add a plugin here in the pipeline. I'm prompted here with whatever is available on the path. So if I zoom in, you see that HiPass is here. So this is the one that we generated. We saw it in that folder earlier on. Okay, and I've got it here. So okay, so exactly as we expected. And actually, we could also add the one that we had before, 3-band parametric EQ. You see, now you know how this worked and why it worked. This is coming from that bit of MATLAB code. Now, you can see that definitely we put some effort into making this simple, not only in terms of workflow, so to make it work, but also simple as a result. That's not your average plugin. That's less than your average plugin. That's a simple thing that looks simple. It didn't require much effort to set up, but it doesn't give you too much. It's something that's good for prototyping, right? And if you have a ton of parameters, you probably want to decide how many you want to expose, because exposing 200 parameters in this thing is not practical, and also visualization is not there. So I don't have a good answer for the 200 parameters. You need to work around that limitation. This is a simple workflow to do prototyping, and that's it. I want to say something about visualization. Again, visualization in a plugin is part of UI design. There's nothing here that I've shown you that had to do with any UI design. We're not making that available, at least not as yet. But if you have some visualizations to do in order to debug what you're doing, there's another set of things that you could do. So you could have this plugin talk to MATLAB under the hood. So let me show you something here, and I'll explain in a minute what this is doing. I got a visualization here, and I've got Reaper here. Okay, so what was going on? Maybe you're tired, and maybe the sugars are going low. Maybe it doesn't surprise you. Totally acceptable. But if you add your attention on 100%, then you would have said probably, what the hell is going on? Because this is Reaper, and then that is MATLAB, and what am I seeing here? So what you're seeing is that this guy, every time that I changed the knob, I had put a Trojan horse inside it manually. Basically, I was collecting the computed coefficients, filter coefficients, and then sending them to MATLAB as a UDP packet. And I was listening and on the fly updating that plot. And this is an example that ships with the documentation. So there's a lot that you can do. The nice thing is not only that MATLAB can talk over UDP quite easily, but also that if you write some code that uses UDP sockets, you can generate a plugin out of it. We wouldn't budge, which is surprising. We don't generate source code for that UDP socket, but we link the code that you generate, so the plugin, to the DLL. So with MATLAB come a collection of DLLs to talk to peripherals. In a few cases, like even for talking to audio, those come in the MATLAB bin folder. And as long as you ship the right DLL with the plugin DLL, then this thing will work. So your plugin will be able to talk over UDP, which can be handy. And this is the reason why I opened Reaper with a command window. I wanted to make sure that it would open up with the right path, so I would know where the DLL was. Right, I've pretty much talked for enough time. I just wanted to show you, please, question.
When you're compiling it, is that all done within MATLAB, or does it call an external compiler?
Okay, so question about compilation, what compiler are you using? So there are a number of compilers. It's a C compiler. So here I'm using Visual Studio. And if I remember well, for plugin generation, we only support a number, kind of 2 or 3 versions of Visual Studio.
Right.
Including, so they did a kind of weird change to their licensing policy, but now we support, again, those that are free to get.
2017 is
Yes,
even
yeah.
the community edition.
Yes, exactly. For a couple of those, we'll support community
Do you know
editions.
if that's going to work over like something like ZenWorks if it's distributed?
Say it again, over?
Like ZenWorks, something that's distributed MATLAB and it's not all installed on the same machine. It's maybe on a central server.
Should do, but I don't remember. I don't remember trying it.
Obviously, because there's a link there going on, and
Yeah.
if it's abstracted from the computer you're using, it could be difficult to get to work
I
around.
haven't tried. I don't have the response handy.
Okay, I'll save that for the technical team.
Yes, exactly.
Do you have
Send it to me. I'll forward it, and I'll let you,
Okay.
send me an email. I'll give you.
Are we going to look at Simulink at all? Or?
I wasn't planning to, but I can say a couple of things.
Because there's audio blocks from this toolbox in there. Can you compile from Simulink to VST?
So, yeah, the question is, can you compile from Simulink to a VST plugin? No, you can. Do you use Simulink, by the way?
Yeah, I do.
Okay.
Teaching, yeah.
Okay, good. You don't have those workflows automated that way. In terms of how you can work together with Simulink with this, in Simulink, there's a number of ways to package blocks that are made with MATLAB code.
Right.
So there's a MATLAB function block, for example, and there's also a new block called MATLAB system block. So what you can do is you can take a bit of MATLAB code that you write to become a plugin, and also make it become a block in Simulink.
Right.
Okay. I can show you. I can show you, for example, where I'm taking that 3-band parametric EQ and making a Simulink block out of it.
That would be
but you can't go from a Simulink model to a plugin. Not yet, not for a number of months or a few years.
So you've always got the stage of writing some basically object-oriented code.
Yes,
to do it.
you've got you at least need you need a shell. You don't need to be an object-oriented programmer, but you need that class shell template
Yeah.
to stick your code in and bubble up the relevant bits.
Okay.
And then from there, off you go. Now the last, so let me save that for later on because it similarly tend to be less popular in general. So I wanted to keep things simple. The last bit that I wanted to show is if you think about plugins, right? I have got another project here where this is actually some recorded voice. So let me do something before I forget. Let me connect left and right channels. Okay, so this is just some.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5.
Okay, did you get what I was doing there? So I've got obviously kind of a recording, which is noisy, there's a bit of hum, and I was using kind of a very naive approach to try to get rid of that background noise, which was a noise gate in this case. It works with very, very feeble noise levels. It's basically saying for anything that's below a certain threshold, so to speak, just shut it down, don't let us listen to anything. So all of these portions here of noise, they were removed. And it's this is kind of a plugin that ships with Reaper. It's called Regate, like Reaper, and this is also kind of a reason why I'm using it, because everybody can then try the code in MATLAB very easily. So this is a plugin that exists. Putting together a noise gate is not a big deal. In MATLAB, there is now a noise gate with the resistant toolbox. So, but think about bigger. Think about having an algorithm that may help you achieve a task. Like, for example, I don't know, an efficient convolution algorithm if you're not happy enough with stuff in MATLAB. An ambisonic encoding algorithm that you can use to do your signal transformation while you're working in MATLAB. Or simply an effect, for example, a noise removal effects that you want to use to process a whole data set that you have. I don't know, is anybody here these days working a lot with, building up huge data sets to use some deep learning techniques or some other AI, right? So data is becoming more and more important, right? So imagine that you want to augment your data set with some effect, and that effect is available as a plugin. Do you see yourself sitting at a door and processing, loading one file and going, adjusting the knobs and then saving it, and then doing again for file number 2 for several gigabytes or terabytes of data for all it matters? It's clearly impractical, right? And the concept of VST plugin, again, I guess when these things were thought about in design, the size of data sets that we have these days was not even imaginable, right? So the concept around VST plugin is all about interactivity. But think that you wanted to use something like that to clean a whole data set. How would you do? So here's the answer for that and all the other things that I said. So look at this, Regate dash standalone. So there's a version of this that's come with a separate download that are actually that's a collection of DLLs. So I got it on my path in this case. It was up here, probably. There you go. Sorry, Regate, this one. And if I execute this line of code, let me clean up this. Look what I have. I have, instead of my plugin with knobs, I have a MATLAB object with all those values already decoded. This is a big deal, having having the actual units in here, because if you go into the guts of the VST plugins, how the parameters are encoded is actually a single value between 0 and 1. And then it's your business to go and understand what that means, because the interface has it clear, has a knob with drawn numbers, but if you're going at the API level, you want to hang yourself. You don't know that. So it's pretty difficult. So in here, you would say hold equals 4, and that would mean 4 milliseconds, okay, right away. So what's the advantage of doing that? Let me show you just a quick example. Is that in this case, in the case of denoising, I'm just running a whole example at once, and it will come up with 2 plots. Remember that counting? So that this is the same counting in log absolute amplitude in the time domain. This is the source that you had here. So noise floor, which is a lot more visible in dB scale here, and assume this is where we want to get, which is the clean audio with gating applied with this noise. So what I was able to do here in MATLAB is to take that signal, do some enveloping of that signal to try to estimate the energy, figure out where there is signal and where there's not signal. Where there's not signal, you see this is the red dots here. Estimate the power value only where there's no signal. Take a value for the noise floor, set the noise floor as a parameter to the noise gate, and process the signal. What's different is that I'm using not my ears, or not an interactive tool, but actual computation to extract a parameters that I can use to set another parameter. And if what I'm doing here is scalable, and it makes sense for my whole collection of files, I have 100 gigabytes of audio content. Okay, for loop, 1 by 1, execute the for loop, and for each loop I will measure the noise floor, set the rise threshold to the noise gate, and the noise gate will process, and I can go grab a coffee, I'm back, and my whole data set is processed or augmented or filtered or whatever. So it kind of, to me, I'm excited because I think as data sets, as data becomes more and more important, it will enable people to get algorithms that have been thought and developed and marketed as interactive to use them programmatically. And the ability to do cool stuff will exponentially, virtually augment.
Can you do that with any VST? Or is it certain ones that allow you?
So can you do it with any or certain ones? Any well-behaved? So this should work with VST 2, 3, and AU2 as well on Mac. Sometimes there are nasty things that happen. So one instance, so these guys, because the people who sell VST plugins, they sell to consumers, they have all sort of crazy ways to check your license. And so sometimes, as you call the plugin, you got a pop-up window that says, enter your credential details. And that breaks this, because that we don't have the interface to give you back that window for validation. So try it before stating that you can do it. Another bad thing that can happen in some cases is that some developers, including these guys that I showed you, they give you knobs, but at some point, people start doing things rigorously and say, okay, I'll abide by the VST standard, and for every property, I'll document it, I'll expose it. Sometimes you say, heck, I need to ship tomorrow. I'll put a knob here, and I use a backdoor to go into my plugin, not going through the VST parameter list. And so there are some cases it happened when I see a plugin UI and it's got 12 knobs, and I look at my parameters, 10. What happens to those 2? They weren't listed using the VST API, so we don't see them and we can't render them as properties. But for all the others, it should do the right thing. That's it. And other things you can do with this, as I was saying, you can integrate something with your MATLAB design. You can test your own plugins you're developing programmatically. You can see that if you're trying to do something that exists out there, you can compare yourself to the third party and see how well you're doing, and this kind of things. And that's pretty much concludes the example. I had a okay, so let me do this. Just to give you the right inspiration to ask more questions offline. So all the things that we discussed, so audio streaming, we basically have been saying, if you write your MATLAB code correctly, that can be formalized as equivalent to a VST plugin. So a VST plugin can be hosted in an environment like MaxMSP and give you a patch. It's if you write your algorithm the same way, and the interface that you give the algorithm is essentially the same of anything that's written to go on a professional tool. And if you, when you import the plugin into MATLAB, it would look to the user like the plugin that you write. So it will have a process method and so forth. The idea here is that if you write things in the right way, then you can get to have, you also get to run in this native, let's say, graphical programming environment is not making it good justice. We call it kind of platform for model-based design, but it's basically a kind of a graphical environment to program system designs. In this case, I've got this template that's just audio. I beg your pardon. Okay, so reading from a file and writing to the sound card. There's the block down here on the audio system toolbox. You can see that there's ways to get audio from sound card using blocks, writing to sound card using blocks. There's filters. So basically for every algorithm that ships in MATLAB, pretty much there's a block counterpart you use in Simulink. Now, there's also ways to plug in your own algorithm. So in this case, this MATLAB function block is very easy to author your own block in Simulink. You drop it in, double click, it will open kind of MATLAB editor function, slightly different from the traditional one. You can see that using this, you can go back to the diagram, which normally doesn't exist. But you basically you write your code to take your input and produce an output, and it's pretty easy. If you are organized in the way you write your code, you can be more ambitious in that when you write your code and you expose your parameters inside here, this is another block called MATLAB system. When you drag it and drop it, you see that it's red and it's all dashed, but it tells you to drop the name of a class that you've written. For example, in that case, it was 3-ban ParameQ. It's found it, okay. And if I hit OK, it will take a minute and create an actual block, not any dashed lines anymore. And if I open it, it's got my values of the parameters with all the defaults, so I can drop it in, and it will take it will take just a moment to interpret the MATLAB code and translate that code into the C code running, and there will be C code running underneath this as well. And as soon as that translation is done and the block ready with the right compiled interface, the model will just run and it'll keep passing. You can see in this case, if you can read here, you will see a 1024 and 1024 by 2 here, so a stereo channel with 1024 samples per block going through that block. And in this case, well, in this case, I'm not investing any time into building an interface. The interface doesn't come in as nice. I would come into MATLAB, but there are ways to tune it from here. Less automated, perhaps, but there's still a lot of automation into building your own block based on this. So the idea is that you author in MATLAB, you can go to plugin, with the same code, you can also drop a block here. But you can't, these days, I'd like to think yet, go from this diagram to a plugin directly. Okay? You don't build your own diagram.
Not even with the Simulink code as well, is it? You can't export
You
C
can,
and then recompile.
yeah. There's a number. So when I say you can't, I think you should take me with a pinch of salt. So regardless, from MATLAB code or Simulink models, you can generate source code. So if you know how to write plugins, you have access to something like Juice. You can take a model like this, select the algorithmic portion, and generate some C code and get it into Juice. Okay, that's always possible. Simulink coder. What I'm talking about here is things that are easy and work right away and are fully automated, and that is not yet there. Good. I think with that I covered all that I was planning to. Let's just make a sanity check, and for the benefit of honesty, just review.
Thanks very much.
Welcome. Thanks for coming. Right, so let's see if I covered all of these things that I was aiming to cover. So how to prototype real-time audio streaming in MATLAB. So in and out from sound card and plugin generation, fine. Real-time custom measurement, you know, it was not among my agenda items, but I think the concept stands. Using the input audio, the audio in and out interfaces can be used to do, you know, impulse response measurement or other sort of real-time measurements. Verify and analyze VST prototypes, or your own prototypes, or others in MATLAB or VST plugins. Existing VST plugins and teach real-time audio DSP array. These were all things that I hope you got away with thinking that you can do, and these were my agenda items. Actually, the agenda items were higher up, but yes, pretty confident we cover those as well. So yes, agenda items were up here, and that's it. Any residual questions? Knock you out of consciousness.
In your, so the process function is the one where your DSP sits and goes. If you've got, so if you have a sample by sample processing loop that you know works, can you stick that in that loop and then it's inherently slower because it's running just in that style rather than something like filter? But you can put something in that loop that's sample by sample.
Yeah, absolutely. I'll repeat your question first. The answer is yes. So the question is, we've seen that the process function inside that object infrastructures was expecting a buffer of samples. Okay, can you stick in there code that goes sample by sample? The answer is yes. You totally can. And as a matter of fact, having buffers, the only reason why that's important is because you read audio and write audio on buffers to the hardware. But inside there, you can do what you want. You should expect, actually, in theory, you should expect that when you write your own class with the process method, you should be able to handle as inputs, as output, any length from 1 to thousands. Okay, it shouldn't be difficult because anything that you do by knowing the size of your input, and you need to form your output by knowing the size. So anything you do. And that can include, of course, sample by sample processing. But as you said, rightly so, whenever you do sample by sample processing, there should be a bit of a light bulb in your head thinking, okay, I can't do that, but as I do that, sure enough, I'll be paying a performance price. And whether that's acceptable or not acceptable, it will depend on what you're doing.
Yeah, just a technical question. OSX supported?
It's yes, yes. OSX, yeah. So, okay. So our OSX supporter. So in a variety of ways, we touched a variety of things, right? So, what were the things that made Mac different from Windows? First of all, audio interfaces. So ASIO drivers don't exist on Mac, but there's Core Audio, which is a very valid alternative. Actually, these days, even more rigorously faithful to what's in the box, because they both develop the same thing, so they can go along well. The other thing is plugin generation that is supported on Mac. So in the generation today, we only generate VST2. That will have a .vst extension, but the workflow is exactly the same, and you would have fewer headaches in terms of compiler support because that's one, and there's no choice there. So that's yes.
So the SDK for the if you're using an external compiler, you would normally have the VST SDK to call from that. Is that included in the MATLAB stuff?
Right.
Then, or
So
do you need it with the external compiler?
So the question is, the relevant one is about the VST SDK. So you don't need to download the VST SDK. You don't need to sign on any agreement because we basically signed it for you. To the extent of what we deliver, Steinberg is already on board, and they're happy for you to do whatever you need to do. You don't need to download it or accept any condition. You just accept the license, the MATLAB license agreement.
So MATLAB will hook into your compiler, give it all the right settings to do everything, and provide you with all the modules it needs, and then just set it away to do
Yes. You don't need to configure your compiler. Yes. Because everything you've seen is how things actually happen. You won't go, so that command that calls generate.all plugin, it's not something that you will go in and hack in and change parameters. No, you will have a few flags to configure there, such as, for example, one important thing that you can do is choose between 32 and 64 bits, because some application only still accept 32 bits. And that will be, after generate all your plugin, it will be a -win32, and that's what gives you 32 bits. Not much more than that to do. Anything else? Well then, thank you very much for coming.